Hi, this is the Physics 2211 lab for report. The topic is oscillations. First, in the next couple of slides, we will be observing and predicting the motion of a mass or an object that is attached to a spring and happens to be oscillating. So we will be using the following applications during this lab: Newton's second law, Hooke's law, and the energy principle. Let me just go through them real quick. First, we have Newton's second law, which demonstrates that the final velocity will be equal to the initial velocity plus the net force over mass multiplied by delta t. Next, we have Hooke's law, which considers the spring force. It is equal to negative k multiplied by s, where s is spring displacement. And lastly, we have the energy principle, which is equivalent to the work, which is also equivalent to the change in kinetic energy. The system is considered to be the spring and the mass. The surroundings include Earth, potential sources of air, could have K prob, a glitch, the tracker software, user misunderstanding of the software and calculation errors. I apologize for the coughing and the sniffles. I'm not feeling my best. I'll leave a comment about that. Anyways, I used the video provided for us on Canvas on the Lab 4 instruction page, and I uploaded it on the tracker. Simple observations that we have. So we have the mass that is attached to the spring and is oscillating and moving in an arc as stated in the instructions. When I uploaded the video into Tracker, I was able to get the position coordinates for the mass. And I have attached an image from the video as a refresher. So now, moving on, let's talk about some of the data. We have that the mass is 0.402 kilograms. The initial position is negative 0.08 meters in the x direction and negative 0.66 meters in the y direction based on my axes. The initial velocity in the x direction is 0.363 meters per second and negative 0.2316 meters per second in the y direction. All this information can be related back to the spring. So using Hooke's law, we are able to calculate the spring constant, which was 6.87 Newton meters, and the relaxed length is 0.127 meters. So for this program, we used a loop, and so I changed a couple of things in this loop. So for gravity and spring force, I was able to get the net force to be a summation of these two forces. Also, through Newton's second law, we can get the ball's velocity and position. We were also able to get the L and the L hat, as well as S, which is just L minus L naught. And we also got the gravitational potential energy and the potential spring energy. And changes in both of them. We are able to solve for delta. Goodness. Now we have the energy versus time graph. I apologize that the image is a little bit blurry, but basically everything that we have discussed is summarized here. So the energy principle states that the change in energy should be conserved, and that is the case here. As you can see, the orange line, which is delta E, is equal to 0. It did not change unlike the individual forces, which are oscillating between the positive and the negative. And just to emphasize this, now we're going to compare the observed versus computational data. So delta E is equal to 0. And as you can see on the right here, we got the graphs of position in terms of time. The blue lines in the models are the ones that we got through the computational data, and the red lines are through the observed data. As you can see, they're very similar. Slight difference between them are due to approximations made by the experiment. And now the x-axis period I calculated is 1.66 and the y-axis period is 1.53. Thanks for listening.